Yo, bro, this water is magic. It bends the spoon.
Oh my days, how are you this old and you still believe in magic? That's not magic, it's refraction. The water is of a different density to the air, so when light passes into the water, it slows down and bends. So that way, it looks like the spoon is bending.
Oh, okay, so it's like when I stick in my shank, it looks like it bends, but it doesn't.
What shank, bro? Your name is Sir Edmund Bartholomew III. Stop trying to act like you're on road.
Today we're going to go through the concept of reflection and refraction. So let's start off with refraction. Now, when a wave travels from one medium to another, so that basically means one material to another material, it will change its path. And here's an example of how that really happens. So let's say I'm going from air into water. Now, air has a much lower density than water, and water is obviously a lot higher density. So let's say I had this light wave traveling here at an angle of theta I. You can call this the angle of incidence to the normal, which is the perpendicular line between the air-water boundary. So this angle here is 90 degrees, and we call this the normal line. When it moves into the higher medium, it bends towards the normal. We call this angle theta r for the angle of refraction. So when going from low to high, the angle of incidence is going to be greater than the angle of refraction. And we can say that the light bends towards the normal. As you can see, it's just moving in the direction that is closer to the normal line. And the opposite happens when you move from high density to low density. So let's say you're moving from the water to air. As the light comes in at an angle of theta I, it will move away from the normal, where this angle is here theta r. Well, you might think, well, how much does this angle change? Well, it's related based on a concept called the refractive index, and it's denoted by this letter n. And what it's given by is n is equal to c over v, where c is the speed of light, or the speed of the wave, which is usually light, but sometimes it can be something else, in a vacuum. So this is in a vacuum. So the speed of light in a vacuum would be 3 times 10 to the 8 meters per second. And this v here is the speed of light or the wave, but again, typically in your examples you'll be using light. And this time it's in the medium that it's going through. So if I wanted to find out the refractive index for glass, I would take the value of the speed of light in air, which is 3 times 10 to the 8 meters per second, and divide it by the speed of light while it travels through glass. And this may give you a value of around 1.5 or 1.6 or 1.7, I can't quite remember. And you don't need to remember any values for exams, except for the fact that a vacuum has a refractive index of 1. So in a vacuum, your refractive index is 1. And for air as well, it is roughly equal to 1. In most cases, you will assume that the refractive index of air is 1. So let's look at an example where it moves from medium 1 into medium 2. And this medium 1 has a refractive index of n1, and this medium 2 has a refractive index of n2. And this angle here is theta 1, and as it moves out, this angle here is theta 2. And we don't need to really specify which angle is bigger than the other. The way these two angles are related to each other is that n1 sine theta 1 is equal to n2 sine theta 2. This here is known as Snell's law. Now there are a couple few tricks that you can do with this equation. We know that n1 or n is equal to c over v. So n1 is equal to c over v1 sine theta 1, and n2 is equal to c over v2 times sine theta 2. And we can cancel the c's and do a bit of rearranging to get that v1 over v2 is equal to sine theta 1 over sine theta 2. Now, one thing that you have to remember is that during refraction, when light passes from one medium to another, the frequency remains constant. The frequency does not change. Only the speed changes. And because frequency is constant, we know that v equals f lambda, so therefore the wavelength will also change. We know that wavelength is proportional to v. So we could also say that the wavelength in one medium over the wavelength in the other medium is equal to sine theta 1 over sine theta 2. So this relationship also stands. This also holds. So now let's say that we're going from a low medium to a high medium. And what we're doing is we're now increasing this angle theta, this theta 1 value. So as it's going from a low medium to a high medium, it's going to refract away from the normal. So this angle here, theta r, is going to be bigger than theta 1. And we know that from n1 sine theta 1 equals n2 sine theta 2. As we keep increasing theta 1, theta 2 is also going to increase. So let's assume the scenario where I'm going to keep on increasing this angle. And now let's say I put this angle such that the wave enters here. Let's call this theta 1. Now let's say in the scenario here, this wave is refracted so much that it now travels along this line, where this angle here is 90 degrees. Well, this is a special case, and this angle here is called the critical angle. And this is where the incidence angle at which the refracted ray will pass along the boundary. So this means that the angle of theta 2 is 90 degrees. So I'm going to now call this angle theta c. So n1 sine theta c, which stands for the critical angle, is equal to n2 sine 90. Now, sine 90 is quite special because it is equal to 1. So what you can actually get is that sine of theta c is equal to n2 over n1. Your critical angle is equal to the ratio of the medium that is going into over the medium that is coming out of. So we now established that what happens at the critical angle, this ray will eventually travel along the boundary. But what if I was more curious and I wanted to see, well, what happens if I increase the angle? What happens if I increase the angle such that it is greater than the critical angle? If theta I is bigger than theta c, if the angle of incidence is greater than the critical angle, what's going to happen is an event called total internal reflection. What that means is this ray will no longer be refracted, but instead it will get reflected back. So it will get reflected back at an angle of theta r, where in the case of the angle of incidence is greater than the critical angle, theta r will be equal to theta I. So when total internal reflection happens, these two angles here will be equal. A very important use of this is in something called an optical fiber. Now, optical fibers are very, very useful because they help to transmit signals over long distances. An optical fiber is made out of two components, a core in the middle, surrounded by something called a cladding. This is basically a cover to the core. So what happens is, a signal gets sent into the optical fiber, into the core of the optical fiber, and let's say it's sent from air, this refracts, let's say, and let's say it refracts towards this normal, so it moves in at this angle. And we want this signal to stay in this core. We want this signal to travel along the core to its endpoint. We want this ray here to reflect back. So we want total internal reflection to happen in the core. So in this case, this theta I value is equal to theta r. And more specifically, we want theta I to be greater than theta c. We want the angle of incidence to be greater than the critical angle. So in order to make this very simple, in order to make sure that we can get as many total internal reflections as possible, we want theta c to be as low as possible. And when let's look at our formula, we know that sine theta c is equal to n2 over n1, where n2 in this case is going to be the refractive index of our cladding, and n1 is the refractive index of our core. Now, for this sine theta c value to be as low as possible, and for total internal reflection to occur, we need the refractive index of the core to be much greater than that of the cladding. Now, if the refractive index of the cladding was greater than the core, total internal reflection would not happen. So not only do we need the refractive index of the core to be greater than that of the cladding, we want it to be as large as we can get it to a reasonable amount, such that we can ensure that none of the wave escapes through refraction. We don't want this to happen. So that's why the cladding here is a very important material in allowing signals to be transmitted, because the refractive index of this cladding is so specific, such that total internal reflection can occur. Now, some key properties of this cladding. The first one is that we want this refractive index of this cladding to be less than the refractive index of the core. But what it also does is that it prevents any loss of info, and we can also use it as a cover, so it prevents any scratches on the core. And this is good. If there are any scratches on the core, if light is incident on the scratch, it is more likely to escape from the core, so the signal being transmitted can escape. And we don't want that to happen. We also want to use a very small diameter for our core, because this way it ensures that the signals do not interfere with one another. This is one of the most important and one of the key uses of knowing about reflection and refraction. This is something that we use in everyday life, such as in transmitting Wi-Fi and so many other signals. So it's good to know about this sort of property. Now, the best piece of advice I can give you after watching that video is to go off and practice on past papers or topic questions. These are single-handedly the best way to help you commit the content you've learned to memory. Obviously, go and do all the YouTube stuff of liking, subscribing, and if you found this video helpful, feel free to go and watch any of my other ones.